Okay, so I'm going to start today just reintroducing some hopefully very important concepts from general chemistry that are going to help you be successful in general organic chemistry, so 235. So there's going to be a couple of these, right? So this is going to be kind of like the start or maybe midpoint of a series of videos that are just there for you guys to go in and peruse at your own leisure. And if you have any questions, I could also maybe just direct you to the videos as well. Okay, so the purpose of this little video is going to be going over or reviewing the concept of formal charge. Okay, so ideally, you learned about formal charge and how to calculate it in 151. And again, I'm just going to hopefully be kind of reminding you or refreshing your memory about what formal charge is and how we calculate it. Okay, so let's go ahead and get started. All right, so there's a couple of things to note about formal charge, and this is just hopefully long-term going to help you guys understand why we utilize formal charge and then kind of what the importance of it is and why it actually becomes a really important thing in organic chemistry. Okay, so number one, formal charge, even though the name suggests that there is a charge associated with something, is not an actual charge. Okay, so if you remember back in, again, general chemistry, if something was charged, it meant that it had either gained or lost an electron, so that it had an unequal or uneven number of protons and electrons, right? So for example, something like the potassium +1 ion, right? If it's +1, that means that potassium has one more proton than it does electron, and that was actually a real charge. We can actually measure that, and it's a real thing, okay? Now, we say formal charge here, but it's not a real charge, and that's kind of an important little thing to note, okay? So even though we call it a charge, it's not an actual real charge, because formal charge, as opposed to things like real actual charges, has to do with molecules, right? And so in molecules, electrons aren't lost or gained in a process like they are in ionic compounds. Instead, they are shared between different atoms, okay? So that's number one. It's not real. Instead, most importantly, it's kind of what we think of as a bookkeeping method, right? So it's just like an accounting method to figure out where electrons are at in a molecule, okay? Now, why is that important? Well, in organic chemistry, frequently, we're going to want to figure out what the products are of various chemical reactions, right? That's kind of like the long-term goal. We've got certain reactants. We want to know exactly what they're going to form, right? And what the actual structure of it is. To do that, to be able to do that, we have to realize that electrons, number one, are kind of like the big players in all of these chemical reactions, right? Chemical reactions occur because electrons move and they go to places that they want to be, okay? And so what formal charge helps us kind of establish is it helps us establish where electrons are at in a molecule, and because of that, we can kind of predict where they want to go, right? So just as a reminder, and I use this all the time, when I draw an electron, I usually draw it like this. So this is representing my nice little electron, and just remember, as you know, hopefully you guys remember, of course, but that electrons are negatively charged, right? So negatively charged electrons usually tend to want to associate with positively charged things, right? Okay, so again, formal charge is going to help us establish where the electrons are at and where they're going to want to go, because they're usually going to want to go to positively charged overall things, all right? Okay, so what else? What else should we figure out about formal charge? Okay, so when we do have a molecule and we're wanting to calculate formal charge, it's important to note that all atoms in the molecule are going to have their own formal charge. It's not a thing that we calculate for a molecule, it's instead a thing that we calculate for atoms in a molecule. So for example, we have our nice little methoxide up here, right? So every atom, the hydrogen, the hydrogen, the hydrogen, the carbon, the oxygen, they're all going to have their own individual formal charge that we're going to actually go through and calculate, okay? Number two, important thing to note, is that when we take a molecule and we sum up all of the formal charges that they have in the molecule, it should sum to the overall charge of the molecule. And I'll hopefully demonstrate that in a second, okay? All right, so let's go ahead. We'll get started in trying to actually calculate these. So when I look at calculating formal charge, I kind of look at it in two different methods, right? So number one, you can quantitatively calculate formal charge, and I give you this nice little pretty equation to do that. I'm also going to explain how like the quantitative understanding or the qualitative understanding of formal charge kind of applies to the quantitative method that I've given you here. Okay, so number one, we have an atom, we're trying to calculate formal charge. The first thing we need to know about that atom is how many valence electrons it has. Okay, so let's start, for example, in our little molecule up here with carbon. Okay, all right, so we want to calculate the formal charge of carbon. I'm going to go ahead and write that out. So we've got formal charge, and then I'm going to use to denote that I'm talking specifically about carbon as a little subscript. All right, so number one, how many valence electrons does carbon have? So hopefully you guys remember how to know how many valence electrons something has. You go to the periodic table, you figure out which column it's in, and it turns out carbon is in column 4, which means there are 4 valence electrons. Okay, so that's number one, 4 valence electrons. Now again, in a quantitative understanding, or a qualitative, I keep getting that mixed up. In a qualitative understanding about this, what we're asking about carbon when we ask about valence electrons is how many electrons does it want, right? So carbon, neutral molecule, has 4 valence electrons, okay? And that's essentially what we're saying. This is how many electrons that carbon wants, right? So number of electrons that the atom wants. That's the first part, how many valence electrons are there. We're going to subtract from that how many we have actually given it in the molecule, okay? So now there are 2 parts to this. There are lone pairs of electrons, or non-bonding electrons, and then there are bonding electrons, okay? All right, so if there are lone pairs of electrons on an atom, we're going to assign all of those electrons to that atom. For carbon, if you know, there aren't any little dots around it, right? So there are no lone electrons around carbon. Instead, all there are bonding electrons, right? There are the electrons that are in our nice bonds right here, okay? Okay, so we've already established how many electrons carbon wants, right? That was the first part of this. But now in the second part, we're asking it how many do we have in the molecule. If there are no lone pairs, then we can just say 0, right? But we're going to add to that all the electrons that are also in bonds. The big thing about formal charge, though, is that when we look at a bond, right, so we zoom in on a bond, what we're going to do is we're going to divide that bond right down the middle, and we're going to give half of the electrons to this atom, and we're going to give half of the electrons to this atom, right? So if you remember, a bond contains 2 electrons, right? So if I give half of it to oxygen, that means I'm giving 1 electron to oxygen, and I'm giving 1 electron to carbon. And we go around and we do that exact same thing for all of the bonds, meaning I get 1 electron here, 1 electron here, 1 electron here, 1 electron here, okay? So in this molecule right now, carbon has 0 lone pairs, but it has 4 electrons from the bonds that are around it. Another way to say that is we could also just say we're going to give it half of the bonding electrons, right? So if 2 electrons are in each bond, there are 4 bonds around carbon. So 4 times 2 is 8, but we're only going to assign half of it to it, so it ends up being only 4 electrons, okay? So we go ahead, we can write that in. We have 0 lone. Now we're going to add in 4 bonding electrons. So we get a 4 minus a 4, which gives us an overall 0 for the formal charge on carbon. Which you're like, okay, big deal, 0, kind of boring. So we can go ahead and write that in here, okay? So that's great, right? But what if something isn't 0, right? What if we have other situations? So now we're going to calculate the formal charge of oxygen. So oxygen up here is this nice little guy, right? Notice there's a big difference between oxygen and carbon, okay? So oxygen has only 1 bond, and now it's got all of these lone pairs, okay? So that's going to kind of affect the calculation that we made for the formal charge. All right, so let's go ahead and we'll get started. We've got oxygen in our molecule. We're calculating the formal charge of oxygen. This is going to be equal to the number of valence electrons. So again, the number of electrons that oxygen wants. If you guys remember, or you consult the periodic table, oxygen's in column 6. So oxygen has 6 valence electrons. Now we're going to subtract from that all that it actually has in the molecule. It wants 6, but how many does it actually have in this molecule? Now, oxygen has 3 lone pairs of electrons, right? And so each of those electrons we're going to assign to oxygen because they sit on oxygen, okay? So 2 times 3 is 6, or you can just go around and count them. This is 6. Now we're going to add to that half of the bonding electrons. Oxygen only has 1 bond, right? And so we're going to give half of those electrons to oxygen. So half of 2 is 1. And so we end up with a 6 minus 7, which gives us a minus 1 charge overall. Okay, so carbon had a formal charge of 0, but oxygen is going to have a formal charge of minus 1. And you can denote that in your little figure up here. Okay, so again, if we went around, we did the same thing for hydrogen. You would get zeros, and I'm going to demonstrate that on the next slide. So overall, what we end up having is a 0, a 0, a 0, a 0, and a minus 1. So this molecule, this CH3O, overall should have a minus 1 charge, right? And so we end up finding out that it actually does. This is what is called the methoxide ion. And it does have a negative overall charge, right? Which is what we'd expect when we sum up all of the formal charge. Okay, so we'll move on. We'll do a little example, and then I'll give you guys another one, and you can do it on your own and come back and compare your answers, okay? So another nice little easy simple molecule we have is ammonium, right? So this is NH4. And hopefully, from your, interactions with general chemistry, you remember that ammonium actually was our only positively charged polyatomic ion. So this was NH4+. There is an overall charge to this molecule, okay? So again, when we get to the end of this, and we sum up all of the formal charges of all of the atoms in the molecule, it should sum to a positive 1 overall, because that's what the molecule actually has a charge for. Okay, all right, so we're going to start with hydrogen. And again, there are 4 hydrogens, unfortunately, in this molecule, which makes a little bit of like, oh, I don't want to calculate 4 different formal charges. I'm going to show you that you don't actually have to do that, but we'll go ahead and start with our hydrogen number 1 and calculate the formal charge for it. So formal charge of hydrogen is equal to, again, number of valence electrons. So number of valence electrons, which is 1 for hydrogen. It's in the first column of the periodic table. And then we're going to subtract from that all of the electrons that are given to hydrogen in this molecule, right? There are no lone electrons, so we don't have to worry about that. And it only has 1 bond. So again, there are 2 electrons in a bond, but half of them are going to go to hydrogen, so that it ends up being only 1 electron, right? Oops, pardon me. That goes down here. So minus 0 plus 1, which gives us a 1 minus 1, which gives us a 0 overall formal charge. So we can go ahead and write 0 here for hydrogen. Now, what's great about this is that all of these hydrogens, right, so this guy and this guy and this guy and this guy, they're all in the exact same electronic environment as the original hydrogen. Right, so that means that, yeah, sure, they have their own formal charge, but when we get back to it, nothing's going to change. It's going to be the same number of valence electrons. It's going to be the same number of electrons assigned to it in a molecule. So they're all going to have the exact same 0, let me switch pens here, 0, 0, 0 formal charge. Right, so if an atom has the same electron configuration around it, it's not going to change its formal charge. So once you calculate one, you know all the others. Okay, so then the last little bit is going to be nitrogen. So we've got our nice little nitrogen in here. So we calculate the formal charge of nitrogen in this molecule. Nitrogen, you consult your periodic table. It's in column 5, so there are 5 valence electrons. Now we're going to subtract from that the number of lone pairs. There are no lone pairs on nitrogen. And then we're going to say half of the bonding electrons. So here we've got 4 bonds. Each bond has 2 electrons, which gives us 8 overall. But again, we're only going to give half of that to nitrogen, which gives us a 4. All right, so we have 0 lone plus 4 gives us a 5 minus 4, gives us a positive 1 overall. So nitrogen is the guy with the positive 1. Right, so again, just as a check, we had 0, 0, 0, 0, and a plus 1. When we sum all those together, we get that nice overall positive charge, which is what we should expect for ammonia. Okay, so I'm going to give you guys a harder example, and then I'm going to tell you to stop the recording and come back, try it on your own, come back and see what the answers are. A couple things to note about this. So everything that we've been dealing with thus far has been single bonds, right? And so single bond has 2 electrons in it. But in this molecule, we're going to introduce double bonds. So a double bond, or let me use a different color. So a double bond is nice double lines here. And just as a reminder, in a double bond, there are 4 electrons. And then there's also a triple bond in this molecule. And in the triple bond, there are 6 electrons, okay? So this example, which I highlight as being hard, which I highlight as being hard, has a lot of different atoms in it, and I want you to calculate the formal charge for all of them in this compound, okay? So pause the recording, come back, and I will give you the answers. Okay, so hopefully you took a little time, you went about trying to calculate this. I'm going to go ahead and go through and give you the formal charge for all of these guys. So it's important to note that, let's say for this molecule, for example, we have 1, 2, 3 different oxygen atoms, and they're all in different electronic environments, meaning they all have different electrons around them. So whenever I'm going through this, and I want to kind of denote that, it's kind of helpful just to give them numbers, right? So let's say that this is going to be oxygen 1, this is going to be oxygen 2, and this is going to be oxygen 3. The hydrogens, you're not going to need to do that for because they're all the same. And the carbons you actually need to do that for. So this is going to be, let's say, carbon 1 and carbon 2. Okay? All right, so for oxygen 1, if you calculate the formal charge for this guy, you would end up with a 0 formal charge overall. For oxygen 2, you would end up with a -1 formal charge. And then for oxygen 3, let me just kind of zoom this out. This guy ends up being something that looks like this. When you calculated this guy out, you would end up with a +1 formal charge, which tends to be pretty bad with respect to oxygen. Just BT dubs. Okay, so all of the hydrogens are 0. Hydrogen won't ever really take on any type of formal charge. We've also got a phosphorus in here. So phosphorus, if I remember correctly, is just under nitrogen. So it has 5 valence electrons. We've got 1, 2, 3, 4, 5. So phosphorus here would have a 0 formal charge as well. So this guy would be 0. Boron's a little different. Boron is in column 3, so this would be a +1 with 4 bonds around it. We've got a carbon with 4 bonds. This is a 0. And then we've got a carbon with a lone pair and 3 bonds. This guy would end up being a -1. Okay? All right, so if you have questions on how I got some of those, please ask me. But hopefully you guys are able to get similar answers. Yeah, and so again, it ended up being a very long review of formal charge, but hopefully this was helpful. And if you like it, you like the content, go ahead and smash that like button, and I'll see you back here next time.